Okay, let's see if we can. Is that better? Shall we begin? Shh. I feel like a robot up here. Let me see if I can move my microphone over. A little bit. Yeah, that works. We are live. We're on YouTube. Hey, everybody on YouTube space. Hi, say hi. Hey. No one's watching, though, at the moment, but someone will watch later. Okay, so there you can look at the slides and have a third-rate education secondhand. Excellent. So today we have a very straightforward lecture on probability, some stuff you've seen before in high school, I hope. And if you haven't, we'll go over it quite basically. It's one of these lectures I hate because I sometimes get it wrong. So, but I'll go slowly, and hopefully we'll all get through it together. Before I start, though, in the lab session, it was pointed out to me that we have some things that are way too advanced for the first couple of weeks. So this is the first time we're doing lab assignments, and the ones that I gave you are sometimes for a little too advanced, like they're for later in the semester, so I apologize for that. But Kahina is on top of it. I understand she gave you mini lectures around confidence intervals and things like that. Don't worry about it. If that's the case, don't worry about it. The lab space is just for you to be exposed to computing statistics and to play around. And you know, it doesn't matter if it's too hard or too easy. It just matters that you're trying and being comfortable using statistical packages, because if you develop a fear of it now, it's hard to overcome it later in life. And if you develop you know, a realization that it's just a bunch of tools that evolve over time, you'll be fine. The problems with the labs, we're not trying to make it hard. We're not trying to make it challenging. We're trying to make it fun in the labs. The exams here are challenging. In the labs, it should be fun and okay, that's all I have to say about the lab space. Yeah, moving on. Good, right? Okay, so last time we started talking about the normal distribution. And we'll talk more about it today, and I'm going to hit you over the head with all these characteristics of the normal distribution that you'll be so tired hearing it for a while. As I mentioned, it's called the bell curve, we call it the Gaussian, the normal distribution is most common. And the reason that we care about it so much is that normality, as we call it, is a natural distribution of a lot of things we see in nature. And it's an unfortunate word, normal distribution, because I've actually seen like you know, papers cited in the lay media and say, well, the scientists said it was distributed normally, but the subjects are clearly abnormal. It's not what we mean by it. We mean it follows a normal distribution. There's something about normal people or normal subjects. So the word gets us in trouble a lot. But now you know what it means. It doesn't mean normal in the sense that this is normal and that's not normal. It means the shape of the distribution is that. So this actually begins, I don't care about the history, by the way. This is just for your, you know, for the breadth of understanding of where this all comes from. A lot of what we understand in statistics comes from astronomy, and it comes from gambling. If you stop and think, even say what's the best application of some kind of facility with statistics and probability, it's gambling. Right? That's why card counting is illegal. Well, not illegal. It's discouraged in casinos. It's kind of weird that you're discouraged from using an ability in your brain. You're discouraged from thinking to make yourself money. It's odd. But card counting is just the use of probability in playing card games. So back in the century and before, top statisticians were often employed as consultants to professional gamblers. One of them was Abraham de Moivre, and he was noticing a distribution of things in card games and coin flips that resembled what we're going to discuss today, normality. And so he probably is one of the first people to describe the normal distribution. He noticed that when a binomial distribution was computed, it tended to look normal. Now, what's a binomial distribution? Binomial means two. There are two things happening. So the classic binomial event is a coin flip. We always use the coin flip as the standard random event, even though it isn't really random. There are elements in the shape of the coin, how I flip it, and so forth, may give it a bit of an edge. But in general, a coin flip truly is random. So in a coin flip, you only get two possible outcomes, heads or tails. Yes, it's possible to land on the edge. There's always some jerk in class that lands on the edge, and once in a million years it lands on the edge. But in general, heads or tails. right? So that's what we call a binomial distribution. And there's only two possible outcomes, except the way that those outcomes happen, depending upon the number of flips, gets more complicated. So a coin flip is what we call a random variable experiment. So it's only two possible outcomes and random. So look at this. Here is a distribution if I flip the coin 2 times of the number of heads that can appear. So how many ways are there in which if I flip 2 coins I get 0 heads? It's only one way. Tail, tail. Right? How many ways in which I get 2 heads? There's only one way. Head, head. How many ways in which I get a head and a tail? There are 2 ways. Head, tail, or tail, head. Right? So let's summarize in this little table here. So if I flip 2 coins, I get either 2 heads, 2 tails, or a combination of heads and tails. So 2 of them, I get a combination of heads and tails. So if I graph it, 0 heads, 1 head, 2 heads, it starts looking suspiciously like the thing we're talking about. If I increase to 4 flips, or 4 coins, how many ways in which I get no heads at all? Only one way. Tail, 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 tail. How many ways in which I get all heads? Only one way. Head, 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 head. 4 heads, 0 heads. How many ways in which I get exactly 2 heads? Well, there's lots of ways. There's head, head, tail, 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 head, 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 tail, head, tail, head, tail, head, tail, head. Right? So clearly you start to see the more flips I get, the more I'm getting this kind of distribution. And if I have 12 flips, I'm getting that. Dun, dun, dun. Right? The shoe drops. So 4 flips, 12 flips, right? So by the time I get 12 flips, suddenly my distribution of possible outcomes start looking normal. So in general, any time I have a binomial event in which 2 things are possible, I get the disease, I don't get the disease. And I get lots of experiments, not just coin flips, different people in my population, millions of people. Suddenly the outcome starts looking like this. Right? That's quite the dramatic finding, that something as simple as a coin flip, when looked at in a certain way, looks like this continuous distribution of a bell curve. So he published this paper describing this phenomenon in 1733. Then it kind of got buried and no one saw it again until the early 20s when a guy named Pearson picked it up. And here's Pearson's name later on when we talk about correlation. There's a Pearson correlation coefficient. But this guy named Gauss, I mentioned a few times, and if you ever study mathematics, Gauss is the great god of mathematics. And he heard about this and dug up through his files and figured out, you know what, I did something like this back in 1809. Clearly, he's already dead by this time this happened, so this happened later. And so he said, I was the first one to do this. Today we call it the Gaussian distribution. It's unclear who did it first. There's evidence that Galileo was on to back in the 17th century. A guy named Laplace discovered the curve back in 1778. So all these people were individually discovering this distribution. And again, it's not a stupid thing to notice, but it's transformed the world in many ways. So Laplace analyzed the curve and took us to this thing called the central limit theorem. And the central limit theorem is really the foundation for inferential statistics. And the central limit theorem, it's difficult to explain, so that's Nemava, if you care. Right? It's got glorious hair, a 5-head. See, it's 4-head, so 1 more than a 4-head, it's a 5-head. Yeah. Here you go. So this is the definition of the central limit theorem. I'll read it first and describe it. It says that a given distribution with a mean of mu and a variance of sigma squared, the sampling distribution of the mean approaches a normal distribution with the mean variance of blah, 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 blah. Okay. All it's saying is, it doesn't matter what I'm measuring. It doesn't matter how it's distributed in the regular population. Let's say I'm measuring height. And let's say the height of the population, if I actually was to measure everyone's height, was like skewed to the low end, so that the average height is actually higher than, there's more people who are taller than shorter, so it's not the distribution that we like. If I were to take a random sample of people and measure their height, take their mean, and I take another random sample of people and measure their height and take their mean, and I take another random sample of people and measure their height and take the mean, and so on and so forth. If I get enough people, the means of each of those distributions, of those samples, if I graph them, it will be normal. That's a remarkable finding. So it doesn't matter how the actual characteristic exists in nature. If I take enough samples of people and measure that characteristics, the mean of each of my samples, when I graph it, will look like a normal distribution. And, miraculously, the mean of all my means will also be the real mean in the general population. Well, that's shocking, too. That's really what this is saying here. It's saying two things. It's saying this distribution of the set of the means of my samples are normal, and it's saying the mean of my big collection of means is in fact equal to the true mean. So I always want to do this experiment in class that I've always been too lazy to actually do, and that is bring like a big jar of jelly beans and have people estimate how many jelly beans there are, and if you get enough people estimating, an amazing thing happens. The mean of your estimate is actually close to the truth, right? Because in general, we sort of average out the errors and get close to the actual truth of it. And that's sort of what we're talking about here, right? Because what we usually do is, or a more accurate way of doing it is I have a mixture of red and blue and brown jelly beans or something, and give each person a random sample and have you count the average number of red ones, and the average number of red ones would actually be the average proportion in the total. Right? So that's the power of sampling. It allows us to do inferential statistics on samples, even if the thing we're measuring is wackily distributed around the world. Okay. So no matter what the shape of the original distribution, the sampling distribution of the mean approaches a normal distribution. So that's that term, the sampling distribution of the mean. I'll say it one more time. The sampling distribution of the mean, is the distribution, the frequency distribution, the histogram, the curve that describes the means of an infinite number of samples that I've selected. Okay. Now, all of this way of thinking, which forms a foundation for every single statistics course that you will ever take, is part of a school of thought called frequentist statistics, because we care about frequencies, we care about distributions. All the techniques that I will teach you are based upon inferring from frequencies and distributions, frequentist statistics. There's another school of statistics called Bayesian statistics, which, to be honest, is probably better, in my opinion. It actually informs more industrial activities and decisions these days, but it's so new in the world that you tend not to learn about it until graduate school, and that's unfortunate. I think there will come a time when that technique will percolate down to undergraduate and high school levels as well. Just keep in mind, on your radar, there's another way of thinking, and I'll give you an example of Bayesian statistics later on in the semester when I have a free moment, because it's kind of cool. It's actually a more intuitive way of thinking about the world, because this is kind of complicated. And sampling distribution is all about. Bayesian statistics really is about taking a guess, refining my guess, taking another guess, refining that guess until I get down to an estimate of what's actually happening. Okay, off on a tangent. So, what does all this mean? It means, yeah, I said this already in better words seconds ago. Okay, let's look at the probability of a coin flip again. It's a random variable, right? We flip a coin. We either get 1 or 0. Here's a probability. We looked at this already. The thing about once I have my distribution of the possible outcomes, my frequency distribution, this is actually a probability density. So your histogram, your normal distribution, it's a probability density. Hopefully you did probability densities in high school. What a probability density tells us is, because this is the way that events are distributed in the real world, for example, 1,000 coin flips, probability of getting of 0 heads, probability of getting all heads, probability of getting like some heads, and probability of getting equal numbers of heads, and so forth. I can figure out the actual probability by taking the area under the curve. This is what this formula says. I'm not going to ask you to do that in this class. I'm not going to ask you to apply this formula. That's finite mathematics. It's not what we cover here. Just be aware that this describes a probability, because this will be relevant later on when we look at sample size calculations, how we compute how many people we need in a study to get a statistically significant sample. It all has to do with estimating the probability of something happening. So, as I mentioned, our normal curve is magical for a lot of reasons. One of them is that we link the frequency distribution, the number of heads and so forth, to probability. It's bell-shaped, it's symmetrical, it's got, on the center, and we say that the standard normal has a mean of 0 and a standard deviation of 1. That doesn't mean that the average person has 0 height. It just means that mathematically we like to have it at 0, then we transform it to match our actual realities. You can go to this site here and play with their little normal distribution applet to change characteristics of standard deviation to see how it changes the shape. I would do that for you, but the computers here don't support Flash, so because why? Why would they? Why would they be accommodating to education? I don't know. So, right. So, in other words, what we call the standard normal or the canonical normal, the textbook normal, is a special case of the normal distribution in which the mean is 0 and the standard deviation is 1. How is this relevant? It's relevant, again, in the transformation we'll do later on when we compute actually not very useful things like z-scores, which we did last time. So a z-score, really, when we compute a z-score, is it's transforming the distribution that you have to resemble the standard normal. So if you remember last time, we said a z-score is your score minus the mean divided by the standard deviation. So if you remember your finite math, all that formula does is transform your curve to resemble a standard normal. Because I'm taking away the mean to bring it down to 0, I'm dividing by the actual standard deviation to bring it down to 1. So I'm just transforming the distribution of marks in my set to resemble the canonical normal. Again, it doesn't matter. If you don't get that, it doesn't matter. I'm not going to test you on that if you care about that kind of stuff. I'm just explaining why we do certain things. But when it comes to actually doing them, you don't really need to understand the fundamental theory underlying it. So remember, the z-score is the number of standard deviations that your score is away from the mean. That's all it is, as we did last time. Right? And we usually report it to 2 decimal places. So why not? Okay, so we did this last time. I showed this slide before. So our standard deviations are, separated away from the mean. So if you have 1 standard deviation below the mean, let's say that's your mark in class, you are doing better than all of these people. And that amounts to 13.6 plus 2.3, which is about 18% of people you're doing, or 16% of people you're doing better than. So the probability of you doing better than everybody else is 16%, in other words. That's probably a distribution. If I'm 1 standard deviation above, I'm doing better than all of these people, 84% of people. So the probability of me doing better than everybody else is at 84%. That's the way that distributions relate to probability densities. And we covered this last time. We mentioned the 3 sigma rule, right? So 1 standard deviation away is about 67%. 2 standard deviations is about 95%. To be precise, 1.96 standard deviations is exactly 95%. 3 standard deviations is almost the entire curve, 99.7. Now I mentioned that's an important number, 1.96, because that gets us to 95%. And why is that important? It's because of that. You ever read surveys in the newspaper and they say the results of this survey are accurate to 95% confidence interval plus minus blah 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 blah. Why is 95% so important? It's not just it's a magical sounding number that we agreed upon many years ago that means something to somebody. We could say that 94% is the important cutoff, but 95 is a round number that humans like. So now 99 and things like that. Okay, so when we compute 95% accuracy and confidence, we are using the 1.96 standard deviations as our umbrella case. Yeah. Okay. Move on. It's blank stares looking at me, so that's my cue to move on and back away slowly. Right. Hey, oh, what's that? What's that? Okay, so I stole these slides from somebody that has animation and sound, so I forgot about this. This will keep you awake. There's going to be a lot of loud noises coming up soon, and it's really annoying. So you 2 people stay. Oh, there's two viewers. All right, don't be afraid. We're going to move now to probability because we've mentioned that the distribution resembles probability. So we're going to take a step back and do some simple probability exercises, and I'll ask you a couple of these questions on the midterm, so do pay attention. Hopefully, you have covered most of this in high school. If not, we're doing it from the ground. Oh, hello, the ground up. I wonder if I can turn that off. Let me see if I can do that. At least bring it down to a manageable level. Okay. Here we go. Sweet. Try it again. Oh, that's better, right? Okay, good. Okay. Oh, this rotates. That's pointless. Right. So probability is a measure for how likely something is about to happen. And we compute likeliness based upon either experience, what we see in the past, or all the possible things that could happen. Oh God, this is going to be annoying, isn't it? So, and in common parlance, probability is a percentage, but mathematically it's a decimal or a fraction. From 0 to 1, where 0 is no chance of something happening, and 1 is guaranteed it's going to happen, right? So certainty versus, oh man, that is annoying, isn't it? Let me turn that off entirely. Okay, put that there. Okay, eesh. That's what I get for stealing slides. Okay, much better. Okay, yay. So, what happened there? Okay, that's exactly what I said. All right, so here we have, oh boy, this is annoying. Okay, we have a spinner, a thing that you spin, and there are things on the thing. Right, so they're labeled A, B, C, and D. So the probability that the spinner will stop on A is going to be, well, it's just 1A over 4 possibilities. So we say it's just 1 over 4. Okay. The probability that it'll stop on an even number, in the case of a spinner with numbers on it, right? There's only one even number here. It's 1 over 3 possibilities, so it's 1 over 3. The probability an odd number, there are 2 odd numbers, 2 over 3, it's 2 over 3. It's 2/3. Right? So here's an example of Lawrence as the captain of his track team. And the team is deciding on we don't care. So he wants to know if Lawrence picks one of these cards at random, what's the probability he will pick blue? So there's 1, 2, 3 blue cards that for some reason are red, right? Out of 1, 2, 3, 4, 5, 6, 7, 8. So 3 out of 8 is a probability that Lawrence will randomly select blue. Okay. So here we have some terminology we're going to go through now. So again, probability goes from 0 to 1, either in terms of percentage or decimal. An experiment in probability is an investigation into measuring if something's probable or not. A trial is one instance of an experiment. For example, the flip of a coin. The outcome is the result of that trial. Was it heads or was it tails? The event is a particular outcome that I care about, either a failure or a success. Maybe I care about heads, maybe I care about tails, right? And the event space or sample space, I use sample space, is all the possible events or outcomes that might happen. I'm going to repeat all that because I'm going to be repetitive today. So again, an event is one occurrence of the activity. A simple event is just one thing happening. For example, a heads resulting from a coin flip. A compound event is when I combine simple events. For example, the probability of getting a heads or a tail on any 2 flips, or something like that. The probability of rolling 2 dice and getting a 6. That's a compound event, right? So the sample space is all possible outcomes I care about. In the case of rolling 1 dice, is it die or dice? What's singular? Singular is die. Dice is plural. Is that right? I get this wrong every single time. Okay, 1 die, 2 dice. 1 die, 2 dice. So if I roll 1 die, I even get 1, 2, 3, 4, 5, or 6. Those are all the elements of my sample space. If I roll 2 dice, well, I either get 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 2, 1, 2, 2, 2, 3, all the way down to 36. So I get 36 possible outcomes. 6 times 6 is my sample space. Right? So the size of my sample space is the total number of all the possible outcomes. A success is the outcome or event that I care about. So if the question is, what's the probability of getting a 6 if I roll 2 dice? Well, a success is a 6. A failure is a not 6. 1, 2, 3, 4, 5. Therefore, all the failures plus all the successes is equal to my sample space. It's a finite set. Obvious stuff. More notation. Capital P is probability, capital A is the outcome. So the probability of this outcome happening is all the number of possible successes over my sample size of my space. Okay, we're going to do some examples. So, right, so here, back up a second. So the probability of flipping heads if I'm flipping 1 coin. How many possible outcomes are there in flipping 1 coin? 2. My sample space is 2, either heads or tails. So if I care about the probability of flipping a head, what is a success? Is flipping a head. Okay. How many successes do I get if I flip it once? I get 1. Probability of getting heads, 1 over 2. Right? 1 divided by 2. So 50%. It's obvious, but that little formula will save your brain when the questions get complicated. So here we go, another example. So if we're drawing one card from a deck of cards, so your sample space is all the elements in the deck of cards, not counting the joker, not counting the instructions, you know, that little thing in the back, right? So you have 52 cards total. You've got 4, what's it called? Thank you, 4 suits and 13 ranks, right? So 2 all the way to ace, right? So what is the probability of drawing a 10 of spades? What constitutes a success in this experiment? A success is getting a 10 of spades. How did I make it red? It should have been black. Okay. All right. So number of possible successes in my deck. How many 10 of hearts are there in my deck? Just 1. Okay. But my sample space, 52. So the probability of drawing a 10 of spades is going to be the number of possible successes divided by my sample space, or 2%. Straightforward. Now let's mix it up. What's the probability of drawing a 10 of any suit? All right, so my sample space is the same, it's the same deck. How many successes are there now? How many 10s of any suit are there? There's 10 of clubs, 10 of hearts, 10 of spades, 10 of clubs, all those guys. And 10 of diamonds. What did I miss? What? Okay, good. Thanks. Right, so how many successes are those? 1, 2, 3, and 4. 4 of them, so the probability is going to be 4 divided by 52. Or 8%. Okay, still with me? Pretty straightforward? Good. Now, we're going to talk about Boolean operator. A Boolean operator are the words and, or not. There are more complicated Boolean operators too. All we care about, though, is and, or, and not. So this happens, and that happens. This happens, or this happens. Or anything happens, but not this. Okay? Now, the way we think about those words in language is great, but the way they work in mathematics can get confusing. So think about this. For example, the chance of rolling either a 2 or a 3 on a die. So I'm saying I will accept as a success either a 2 or a 3. I'm being embracing. I'll take either this or that. Am I being more inclusive or less inclusive? I'm being more inclusive. I should get more successes if I'm saying or. My probability should be higher if I'm saying or, because I'm saying I will take this or that, or that. I love everybody. I'll take all y'all. This or that or that. Or is inclusive, so or should be more. Or I add. Or is add. Okay? It's amazing how many people will forget this in the tension of the moment. Or is and. So the probability of rolling a 2 on my first die is 1 out of 6. 1, 2 out of 6 possibilities. The probability of rolling a 3 on my second die is 1 out of 6. There's 1, 3, and 6 possibilities. So the probability of rolling a 2 or a 3 is going to be 1, 6 plus 1, 6. Because I'm inclusive. I love them both. I'll take the 2 or I'll take the 3. And I get 1 out of 3. That's the probability of rolling a 2 or a 3. As opposed to the and. In the and, I'm being restrictive. I'm constraining possibilities. So the example, if I'm rolling 2 die again, I want the chance of rolling 2 on both of them. So I'm being very exclusive. And is exclusive. So if I'm only going to take those cases in which both of these guys are 2, I should have a smaller number of successes. And means smaller. We use multiply for and. Because we multiply 2 fractions, we're going to get a smaller number. So the probability of getting a 2 on the first die is 1 out of 6. The probability of getting a 2 on the second die is 1 out of 6. I multiply them, and I get 1 out of 36. Okay, straightforward, but you will forget. Or is add, and is multiply. Right? Then there's not. Not is what's left over. So the probability of not getting a 2 on a die is 1 minus the probability of getting 2 on a die. So all not means is you subtract everything from 1. Because the probability of everything happening is 1, probability of everything but not this is the 1 minus the probability of this. Okay? Very useful rule when things get really complicated, as we will see. So that's pretty straightforward. The question gets complicated when we have to combine our Boolean operators to make it all work. So we have to keep track of what we're doing and don't get confused. So first obvious example. The probability of rolling, I use the word chance and probability as interchangeably, but some sticklers will say they're different, whatever, the same. So the chance of rolling 2 dice and getting a 2 and a 5. All right, automatically I've confused you, thrown an and there. So here are the possible successes. On die 1, I can have a 2, die 2 a 5, or die 1 a 5, and die 2 a 2. So those are the possible successes to get a 2 and 5. Out of how many? How many possible ways are there to roll 2 dice? 36, right? So I know the answer is going to be 2 out of 36 already. Okay, so let's break that down though. So the probability of getting this first one is 1 out of 36. Why is that? Because the probability of the first one being 2 is 1 out of 6. The probability of the second one being 5 is 1 out of 6. And I multiply them because they're an and. I get 1 out of 36. The probability of the second outcome is also 1 out of 36. Because the probability of getting a 5 is 1 out of 6. And that's 1 out of 6. I multiply them and I get that. But I will take either one of these 2 scenarios, either this or that. So I'm going to add these 2. Right? And I get 2 out of 36. Okay. That's the long way. Or I could have said, here are 2 outcomes out of 36. Bang, I got the answer. Yeah. Are we clear so far? Very good. Right, now it's a little more complicated. Here we have getting a 7 on 2 dice. What are the different ways of getting 7 on 2 dice? Here are all the possible ways. 1, 6, 2, 5, 3, 4, 4, 3, 5, 6, blah, 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 right? So the probability of each of these happening is 1 out of 36 because the probability of one happening is 1 out of 36. The probability of this one happening is 1 out of 36. I want both of these to happen. That's an and, so I multiply them. The same for this scenario. I multiply them. This scenario, I multiply them. Now I will take any one of these possibilities. This or that, or that, or that, or that, or that. So I add all these up, and I get 6 out of 36, or 7%. So the probability of getting a 7 on 2 dice is 17%. A useful number to know if you're playing craps, right? So try to make this relevant to your life. I don't know if you play craps, but there you go. Okay. Moving on. So clear? Right on. Right on. Okay. Examples. Which of the following is a sample space when 2 coins are tossed? Which is, give me a hand. It starts easy, gets harder. Which of these is the sample space for 2 coins tossed? All possible. So someone said that. You saw a hand there? Yeah, maybe. 1, 2, or 3. Which one is it? 4? That's right. People are so shy today. Well, for 2 coins, we need 2 outcomes each. So obviously it's going to be this one. This is only with 2 outcomes each. Either I get 2 heads, heads and a tail and a head, or a tail and a tail. Right. So that's the answer. All the possible outcomes when 2 coins are tossed. Okay, at Kennedy Middle School, 3 out of 5 students make the honor roll. What is the probability that student does not make the honor roll? Application of the Boolean operator not. So the probability of making the honor roll is 3 out of 5, or 6, right? So not making the honor roll is going to be 1 minus 0.6, which is 0.4, or 40%. Straightforward. A large basket of fruit contains 3 oranges, 2 apples, and 5 bananas. If a piece of fruit is chosen at random, what is the probability of getting an orange or a banana? Okay, like all these things, I want you to think of sample spaces and successes. First of all, what's the sample space? What number is a sample space? 10, that's right. There are 10 pieces of fruit in total. Okay, how many successes are there, given that a success is a banana? 4 bananas? Orange or banana, sorry, orange or banana is 5 bananas, 3 oranges. So that's 8. 8 out of 10 is our answer. There's no 8 out of 10 here. So there's 4 out of 5. Yeah? With me still? Good. Okay. Sorry, what's wrong? No, all right. Someone's having a drug reaction. Okay. So we have a pair of dice is rolled. What is the probability of getting a sum of 2? How many ways are there to get a sum of 2 on 2 pairs of dice? It's only one way, snake eyes, right? And how many ways are there to roll dice? 36 ways. So 1 out of 36 is our answer. So this is the number of ways to sum 2 dice. On this chart here, you can see there's only one of them gives you 2. If the question was probability of getting a 3, well, 2 of these give you 3. Nothing else does, so it would be 2 out of 36. If it was 4, 3 out of 36, so forth. Okay. In the United States, 43% of people wear a seatbelt when driving. If 2 people are chosen at random, what is the probability that both of them wear a seatbelt? 18%. How'd you get that? Sorry? It's on the screen. Ah, look at you trying to do it. No. Okay, explain to me why. It's 18%, that's correct, but why is that true? Is this an or an and question? So I've got 2 people. So I've got a sample size of 2 here, right? Right. So one of them has a 40.43 probability of wearing a seatbelt. The other one does as well. Do I add those numbers or multiply them? This is how the or and ands get complicated, right? So am I constraining things to happen, or am I being embracing and accepting things to happen? I'm constraining. So I need them to multiply. I require that both of them wear seatbelts. 43% of 43% is 18%. Right, so that's how it gets complicated pretty fast. Okay, in a shipment of 100 televisions, 6 are defective. If a person buys 2 televisions from that same shipment, what is the probability that both are defective? Same question. Okay, so we have 2 televisions. The probability of one of them being defective is 6 out of 100, or 0.06. So the probability of both of them being defective is going to be, do I multiply together or do I add them? Multiply, because it's an and question. So 0.06 times 0.06 is 0.0036, which if you convert the fractions is 9 over 2500. All right, so there it is. So pretty straightforward stuff. Now we get a little more complicated. The probability of rolling at least 1 6 with 2 dice. Hey, how many ways are there to roll at least 1 6? Well, there's 1 6, 2 6, 3 6, 4 6, 5 6, 6 6, 6 1, 6 2, 6 3, 6 4, 6 5, and so forth. Add them up. I can do it the hard way and make all of these possible combinations and see, here's a 6, there's 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 a 6. All of these are 6s, right? I add them all up. I could do that, right? So I have 11, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 events that are successes out of total 36. Okay? So when you're in doubt, when you're trapped, when you're running out of time on the exam, when you're freaking out, this way always works. I call it the brute force method. You count up all the possibilities, you count up all the successes, and you divide them. It always works. It's fine. Okay? There's a faster way. And the faster way is rolling at least 1 6 is the same as looking for the probability of not rolling 1 to 5. Whew. Think about that for a second. So let's break it down. The probability of not rolling a 6 on the first die is 5 out of 6. Because in one die, there's 6 possible outcomes. 5 of them don't have 6s. The probability of not rolling a 6 on the second die is 5 out of 6. Same. So the probability of not rolling a 6 on both die, am I constraining or am I? I'm constraining, so I'm multiplying them, is 25 out of 36 is a probability of not rolling a 6 on both of them. Now, but I care about the probability of rolling a 6 on both of them, so I subtract that, and I get 3.6. Same answer. Okay. This is obviously the intellectually more challenging answer. The other one is the brute force method. It gets you to the same place. So 2 dice are thrown. The probability that at least one of them shows a number greater than 3. This is going to be tough. Probability one of them throws a number greater than 3. So let's break it down. Here are all the possible outcomes again. How many of these have numbers greater than 3? Well, this one does, this one, these three do, these three do, these three do, and everybody else does. Okay? So I can add them all up. I get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, plus 19. So it's like 28. Yeah, I think so. So out of 36, 27 rather, right? So 27, all these are 27. I can divide that and I get 75%. That's the brute force method. Okay, that works every single time. It's fine. It's intellectually fine. If you want to be a little more challenging, we could say the probability of showing at least a number greater than 3 is the same as both of them not showing 1 to 3. Do you see the logic there? If I'm showing at least one of them that's greater than 4, the opposite is that none of them are showing 1 to 3. So if we compute the probability of the first one showing 1 to 3, right? I'll accept either 1 or 2 or 3. Those ors, I add them all up. So the probability of the first die showing a 1, a 2, or 3 is 50%. That makes sense, because the rolling die, I'm either getting 1 to 3 or I'm getting 4 to 6. The probability of the second die only showing 1 to 3, same thing. Okay, but if I care that both of them are only showing 1 to 3, I multiply it and I get 25%. Right? Now, if I care that both of them are not showing 1 to 3, then I subtract that from 1 and I get 75%. Same answer, just a little more challenging method. Brute force works fine. I'm a fan of brute force. It works fine, especially in tension moments and stress moments. Okay, right now it seems obvious too. You're going to go home and try this. Like, I don't know what's happening. So just take a deep breath and try again. Right? So your homework is to try those questions. And a couple of these are going to be quite difficult, but you know, and on an exam question, it won't be nearly as hard as these. The hardest I'm going to ask is like this. But if you can handle the hard ones, you can handle these. That is all. Blank looks great. Still with me? Great. One viewer. We lost somebody.